I would like to start with a little thought experiment, and then I'll dive into the hard matter. So all sit back and relax, maybe close your eyes, although not for too long. And just imagine that you are a few years into the future. And, I see people actually dozing off now. That's not the right thing. And imagine that you just bought your very first quantum computer online. Maybe it was something like you wanted to try it out, and you saw some ad, and then you just went for it and bought it. And then a few years later, a few months later, because it takes a while to build these things, a big black box arrives at your doorsteps, and it says quantum computer, and you're actually very excited about this thing that it arrived, and then you start to get some doubts, because actually you have no idea what to do with it. And actually it was also quite an expensive machine. You had to pay quite a bit of money, and then you frantically start to search the web, and you do Wikipedia, and you look up the words quantum programming and quantum algorithms and quantum applications, and it turns out that actually it's not so easy to program a quantum computer, as we will see a bit later in the lecture. It requires completely new ideas and new techniques, and also it is not entirely clear what it's good for, though we do have a couple of things that we think that is going to be very useful for, but not for everything. So, and this prelude, or this dream that you could buy a quantum computer online, is actually already happening. And small machines of about 50 to 100 qubits are available, and already the big companies like IBM, for example, announced that they have 400 qubits available, and so this is growing almost exponentially every year. So this is not really something that we can wonder about in a few years, but something that we have to wonder about now. If this quantum computer is there, what are we going to do with it? And roughly what we want is somehow these two items working. On one hand, we want to have very good quantum hardware, and on the other hand, we want to build software that runs on there that then somehow solves quantum applications, whatever they are. We will see in a little while what they are. And this is in a nutshell what has to happen. And there sort of should be an interplay between, on the one hand, the people who build these machines and who build the hardware, and then on the other hand, people like me who think about applications and algorithms and software. Okay, and actually it's a very exciting times already. I mean, you heard that there was 2.5 or 4 billion pounds, I assume, put into the British quantum computing industry. And it's really a little bit as in the early 60s, late 50s, when conventional computers were getting built and were being built, and people had no clue basically what that would lead to, and if they could look at how the world is now and how it depends on computing and computers. That was not, they were not able to foresee this. Maybe some science fiction writers could get a glimpse on that. And in a way, in the quantum computing era, we are in that same phase, and we are still very much exploring and figuring out what to do. So what I want to talk about today is the following. The title is From Theory to Reality. So I want to go back to the old days of when quantum physics was explored and defined, and also at the same time computer science formalism was being built, and then somehow combining these two gives you quantum computers. So that's all very much theory. Then I say a little bit about how to actually program these quantum computers, how that looks like, and what you have to think about. Then this is sort of a very interesting topic that I'm also working on, but the whole field basically is working on that. What computational problems have a quantum speed up, so it can be faster or more efficiently solved on a quantum computer. And I say a little bit about communication networks and quantum cryptography, and then I'll end with some unexpected side effects of quantum computing that are already happening, and also I'll sketch a little bit the situation in the Netherlands and in Europe on quantum computing and how we are trying to interact and make things work. Okay, so quantum software is really different. I want to make this point one more time. So classical computing has been basically the same from the abacus to the supercomputers that we have nowadays. I guess this one is in Japan, and they all operate on bits, which are entities that are 0 or 1, and that's basically it. And then there's a whole theory around that. And quantum computers really work fundamentally different. For now, let's think of them as qubits. I mean, they're called qubits, quantum bits, that can be 0 and 1 at the same time. And we will see why you can think of them like this and how it's also a little bit different from this. And it requires really completely different concepts to build these machines, but also to program them. And we are really exploring and trying to figure out how we can tap into the power that lies hidden in these machines. And as I already said, there are quite a few interesting feats on the quantum hardware front. For example, Google had a few years back already, in 2019, they had a first claim that quantum computers could do something that classical computers cannot do. So that was really a milestone. They built a 53 computer, and they just let it do a task, not an interesting task, but a task that was very hard to simulate or to do classically. And they claimed that classically this would require 10,000 years to do on their Sycamore processor. But IBM, also in the business of computing and quantum computing, they quickly claimed that they could actually perform this computation on their supercomputer, their IBM Summit, in 2.5 days. And I guess they're right. And nowadays there are techniques called tensor networks that allow you to actually do these calculations on your laptop. So the claim of Google wasn't entirely true, but nevertheless I think this was a big step and a big establishment to do this and to have such a big machine already, 53 bits, working sort of nicely together. Then actually we will hear later today from Professor Pan, who was sort of the leader of this experiment where they built a quantum computer on lights. They did something called boson sampling, and you see here sort of a huge experiment, and I'm sure that he will say a little bit more about this later today, where they had 70 qubits, and nowadays I think they have even bigger experiments. But then again, the question is this true advantage? And the problem is that there is noise in these experiments. They're sort of not entirely stable. And so when you add noise into the mix, then you can simulate these things potentially classically. For example, if you put complete noise in there, so that you only get random zeros and ones back, then you can do that also classically, right? So if there's too much noise in your system, you can simulate it classically. And a deep and interesting question is when and where is the cutoff between not too much noise and not being able to simulate it anymore. Anyhow, so Google raised some issues, and sort of there's a debate going on when we finally will have quantum advantage. In the meantime, there's also a bunch of quantum startups, hardware startups. For example, IonQ is one, and Rigetti is one that actually is having a little bit of trouble now. But Xanadu, and you see that these machines, that these companies really raise quite a lot of capital, and sort of are trying as hard as they can to build quantum computers. Also Amazon is into the game. Here's one interesting one, Quantinium, that's Honeywell sort of merged together with a company called Cambridge Quantum Computing. But here's a Finnish one, and you see that sort of they're all over the place. You see startups and big companies sort of diving into this field. So it's super interesting and nice. But of course, you would like to know, how does this all work? How can you do computation on these machines, and what actually are they? So in order to look at that question, I think we have to get back to the field of physics, and specifically the field of quantum physics and what that is and why it's there. It's sort of a theory that, that started in the early 1900s, and famous names are attached to this, like Schrödinger and Einstein and Bohr. And they came up with a sort of an extension of our classical physical theory called quantum physics. And I'll try to run by you three principles, namely the superposition principle, the interference, and entanglement, to show you that with these three principles you can do very interesting and new things, namely quantum computing, and also why we need that extension. So without further ado, let's talk about this superposition principle, which really says that an object can be in a superposition of two different states at the same time. So it's one object, for example an electron, and usually it happens with very tiny objects, an electron, and that can be, for example, at two places at the same time. So this is not something you encounter in your everyday life, at least not consciously. And this can also be with larger things, for example with molecules, and this has been experimentally verified day after day, week in, week out. People do experiments that somehow verify and corroborate that indeed this is what is happening, and what this is I will show in a minute. It's very counterintuitive what this should mean. It's hard to reason about it from a sort of a philosophical point of view, but luckily we have a very precise mathematic description of the whole thing that allows us to calculate and to know exactly what's going on, and then we can do our experiments to see if they corroborate this theory. So although it's counterintuitive, we have mathematics, and that is very, very precise, and that helps us along the way. I often hear, what does this all mean then? And that is really philosophy, and that's not my area, but it's interesting to think about, but that's not what we do. We do mathematics and we calculate on these things. Okay, so a famous example is of course this cat of Schrödinger that he put into a box with some vial of poison and some radioactive material that would decay or not, and not at the same time. And then of course this cat, as he said, it's a thought experiment, he never did it by the way with a cat, is both dead and alive at the same time. And of course there's nice cartoons like this one. Okay, so let's do the experiment of the cat that is both dead and alive, but not with a cat, but with something more animal friendly, namely light and photons. So let's look at this experiment that I have here. I have here I drew a gun, but it's sort of an experiment where you can construct single photons. So it's basically like you have your light source and you can dim the light more and more, and you can dim it, and this is not easy, but you can dim it so far so that only single photons come out of your lamp, and that is what's happening here. So I have a lamp that shoots single photons. When I push the button, one photon comes out, and I'm shooting this photon at this blue material here. That is a little piece of glass called a beam splitter, and it's really like a piece of glass, so you can look through it and the light can go through it, but it can also reflect from that same piece of glass. And so when you shoot the photon, a little bit like if you look through the window in your house, and you can both look outside the window and you can see also the reflection of yourself and your room into the window as well, right? The light reflects and goes through. That's what's happening here. And what quantum physics says, quantum mechanics, it says that the single photon now at the same time goes through this little piece of glass and it gets reflected. And this is how it looks like. So it's like the cat that is both alive and dead at the same time. And then on either end here I positioned two detectors, photo detectors, and they can detect if there is a photon or not. And if there is a photon, they will click and say, I saw a photon, or they won't click, and that means they didn't see a photon. And now when I run this experiment for a little bit further, so these photons, or this photon that is in superposition, has the ability to reach this detector, we will see that only one of the two detectors clicks. Quantum mechanics says what happened here was a collapse, so this superposition collapsed into either the photon being at detector 0, in which case it had gone through the light, to the beam splitter, to the piece of glass, or it reflected and it didn't reflect in this case. So we can run this experiment one more time, and or we can run it actually many more times. Again, quantum mechanics says it goes into a superposition, but now we detected detector 1. Detector 1 clicked, which somehow means that the cat is dead. And we can do this many, many times, and then you will see that about 50% of the time detector 0 clicks, and 50% of the time detector 1 clicks. Now that looks interesting, and quantum mechanics says that this is exactly 50-50. It's a chance a half of a 0, chance a half of a 1, which actually is something that's useful already in its own right. So here we see the first application of, well, maybe not the first, but a application of quantum mechanics and quantum computing. This is a device built by Idée Quantique that generates random bits. And random bits are actually useful in computation in general. And so here we have a device that generates purely random bits that are 0 and 1 with equal probability. And this is something that is actually hard to get by with a normal computer. And I actually bought this one. I didn't bring it along, but I have one at home, and it's actually amazingly simple. You just plug it into your computer, and you can get a little interface like this, where you can say, I want to generate, here I said 1024 random bits, but you can do more, of course, if you want. And then, boom, out comes a list of zeros and ones that it claims are completely random. Great. So these are, in the honor of the Physical Society, these are freshly generated random bits. Unique, well, not unique, but almost unique in the world. But of course, now you can ask, are they really random? And there's also a nice cartoon about this. And of course, this is a whole different question. How do we check that things are really random? All we can do is statistical tests and see that, for example, the frequencies of zeros and ones are right, or the frequencies of blocks of zeros or blocks of some other pattern. And all the tests that you can think of, this machine passes, so it is probably random. But it could be that someone from above, or that it was already predetermined what the outcome of all these bits were going to be. And of course, we can never distinguish between these two situations. But now again, we're delving into philosophy. Okay, so that's superposition. It says that we have this object, in this case light, but it can be anything that can be in two different states at the same time. Now I want to have another phenomena called interference, and I want to describe that. And actually, I want to go back to the experiment we just did, and I said that this photon was detected at detector 1 half of the time and at detector 0 half of the time, and that it happened with this superposition, and you were all sort of believing me, I think, or not complaining about that this was weird. But maybe in the back of your minds was that maybe there is no superposition going on at all. Right? Maybe just this photon, it happened to half of the time go through and half of the time get reflected. Maybe because I didn't quite put it at the same position every time, or maybe something moved, or maybe it's sort of like with chance it sort of bumped up and with chance it went through, right? That would be a very classical explanation that you feel much more comfortable with, that could explain this behavior as well. Right? So why is it not like that? Why do you need this strange superposition principle? Well, let's make the experiment slightly more complicated, and let's add a few more elements, actually 2 elements of the same type. So let's put some mirrors here, so these really reflect perfectly the light, so nothing goes through. And let's do the same experiment with the photon source here. Here again are these little pieces of glass, and we put the detectors here and here. And by the way, this is called the Mach-Zehnder interferometer, and this is something that you can do in the lab. So let's explore this idea of the 50-50 beam splitter that we have here. And so what is going to happen when we shoot this photon into this system? Well, let's let's do a run. Let's see what happens. So here I'm shooting it. Now, again, it's not in superposition anymore, but it takes one of the two roads. So let's say it took the upper one, but could have also argued the one going through, but let's take the upper one. So this photon now reaches the mirror, then gets reflected by the mirror and enters this beam splitter. I mean, it's about to enter the beam splitter. Now, what do you think is going to happen when I push my button one more time? Which of the detectors is going off? And any on-takers? What's happening here? Well, this is exactly the situation that we had a minute ago on my slide, where I have the photon entering, a single photon entering a piece of glass here. And so if you reason classically, 50% of the time this detector should go off and 50% of the time that detector should go off. Right? I mean, that's what you would say, 50-50 again. That's how it should go. Okay, so now let's do the experiment. And when you do it in the lab, you run it. And then it turns out that detector 0 only goes off. Never do you ever see detector 1 clicking. So how can that be? So clearly, at least this 50-50 interpretation is not correct. Right? Because the 50-50 interpretation would imply that we would see 50-50 also in this experiment, which we don't. So that's not anymore a viable theory that we can use. So according to quantum mechanics, this is what happens. This photon goes, and I told you before, it goes into superposition. And so the single photon goes, it takes both of these paths at the same time. And then these paths combine at this point. And now what happens, and you can calculate that, is something called interference. So these paths interfere. And the paths that go up, so there are two paths that go up, namely this photon that goes through and ends up here, and this photon that gets reflected. They cancel each other, they interfere negatively, and the ones that go through, so the other paths, this photon, sort of this superposition of this part of this photon that goes through, combines with this one that gets reflected, and they interfere positively in such a way that you only see the 0. So what you have to take out of here is that an object can be in superposition at the same time, and it can also interfere with itself to get this kind of behavior. So detector 0 always clicks. So that's interference of one object. And then the last thing that is very useful is a thing called entanglement. And by the way, the Nobel Prize of last year was awarded to Clauser, Zeilinger and Aspect, who did groundbreaking experiments starting in the 60s, late 60s, but also more recently, that actually show that the world is like this, is entangled. And what's entanglement? And here it's slightly more difficult to explain how to make entanglement, and I'm pretty sure that Professor Pan will show us how he did it. But think of it like this. You have now two photon sources like this that shoot a photon into a slightly more complicated setup that I'm not showing how it works, because it would be complicated and not very interesting for this point of view. But out of the machinery come two photons, again, the same ones that went in, and they are now what is called entangled. And without saying what it mathematically means, let's look at what happens when I do the same experiment as before. So I let these two photons go onto these two pieces of glass, these two beam splitters. Well, then one locally here, what you expect is that you see 50-50 beam splitter detector answers, right? 50% 0, 50% 1. And that's indeed what happens. So quantum mechanics says these photons go in superposition, and either this detector clicks or that detector clicks. But here the weird thing is that if here detector 1 clicks, then we will see also that the other detector 1 will click. And for example, if we do it again, then in that case detector 0 clicked. So we see a 50-50 detector 1, detector 0 click on each side, but they're very correlated. So when one detector clicks 0, the other also clicks 0, and one clicks 1, the other also clicks 1. And now the strange thing is that this also happens when I let these photons be very far away. So it could be that this experiment is performed here in Cambridge, whereas this here is performed, say, on Mars. And so there's no time for the information that the outcome of this experiment was 0 or 1 to go all the way to Mars. But nevertheless, if you do the experiment on Mars, you will see that the same outcome will be seen there. And so here's something very strange going on, and this is called entanglement, and this can be used, these strange correlations can also be useful in computation, but also in communication and in cryptography. So I will say a little bit about that later on. So these are the three phenomena: superposition, interference, and entanglement, and that form somehow the cornerstone of quantum computing and quantum information. Okay, so that's quantum physics. Then I also have to say a little bit about computer science, which actually was developed at the same time. Somehow the most famous and best known paper is that of Alan Turing, as you all know, I guess, because he was British, who in 1936 laid the foundations of modern computer science by developing a theory, a mathematical theory, very much like quantum physics, but now not for quantum physics, but for computation. And actually he was not alone. There are two others, namely Alonzo Church and Emil Post. As you know, Turing died miserably because he was homosexual, and that was not tolerated at the time. Luckily, he has been sort of honored more recently, and he's also now, I think, on one of your banknotes, very fittingly. I guess he's my hero, at least. Then the other one is Emil Post, who actually was ahead of Turing, who had earlier already a good definition of what computation is, but he wasn't quite sure whether it was complete. It was, but so he didn't publish. And the other one is Alonzo Church. By the way, Emil Post also died miserably. He was very depressed. But Alonzo Church lived long and happy. So I guess it's not all bad in science world. Okay, so what did these three gentlemen did, and I'm now focusing on the work of Turing. They came up with a model of computation, which nowadays we call the Turing machine, which is a mathematical model of what it means to do one computation step and what kind of operations you can do. And in that same paper, Turing not only defined the matter, he also demonstrated that there are problems out there that cannot be computed on a Turing machine. And the problem actually you encounter almost every day. That's called the stop problem, and that's the following thing. When you do a computation on your computer, very often this happens, right? This little clock comes and it says, please wait, and then you're waiting. And wouldn't it be fantastic if there was a little app at the right-hand corner of your screen that said, you have to wait only 5 more minutes, and then the computation is done and you will get your answer. Or it will say you have to wait 3 weeks, then the computation is done. Or the computation never stops, and you better stop it now because you can wait till forever. Turing showed that such an app is fundamentally impossible to have. So you cannot have a program that tells whether another program will stop or not. This is called the halting problem, and this is about showing the limitations of what computers can do in theory. Even if you had unreasonable amounts of time, you cannot solve this halting problem, this stop problem. However, we're not really interested in real life whether a computation stops or not. We want to know whether a computation quickly stops and gives the answer, or takes too long. So we're interested in quick solutions instead of a solution at all. And an example of that is to find the shortest way from Amsterdam to London. And this is a problem for which there exist very fast and quick algorithms. As you all know, maybe even coming here, you used your Google Maps or your GPS system to route you from where you were to this location, and that very quickly gives you the shortest route. from where you were to where you want to go. By the way, this is due to an algorithm of a Dutch guy called Edgar Dijkstra, who in 1959 came up with this program actually at the same place where I'm working at the CWI. And he also got the Turing Award, the Nobel Prize, I guess, for computer science. And there's this nice quote. He says, "I became the programmer of the Mathematical Center, which is now called CWI, in March of 1952. And they didn't have computers yet. They were trying to build them. And then he came up with this algorithm, and that should remind you of the situation we are in now with quantum computers. They're trying to build them, and we are trying to program them. And look, this was a very good algorithm because it's still used. And so now we enter a little bit into the problems and the interesting caves of computing and computer science, because now we want to know, when does a problem have a quick solution and when does it not have a quick solution? And that's actually very tricky and a difficult question. For example, if we change slightly the question from the shortest path, the quickest route from Amsterdam to London, to the longest, right? Like let's say we wanted to know that answer. And of course, I don't allow switching back and forth between two cities, because then I could make it always infinite. You can only visit each city at most once. Then the longest path actually is something that takes a lot of computation time. We don't have a fast algorithm for that. We don't know of a fast algorithm for that. And the best algorithm we know requires exponential time. And exponential, you probably know how that goes. Now with COVID, also we've seen this exponential growth with this R0 being larger than 1. But basically you also know the chess example, where on the first field you put one grain of rice, and then the second one you double it, and each consecutive one you double the amount of rice that was on the previous one, until at the very end you have an astronomical almost amount of rice, namely 92 billion tons of rice. And if you had actually two chessboards, or 5 chessboards or so, then and you had 300 tiles, then you would have 2 to the 300 rice grains at the last field, which is more than the number of atoms in the universe. So this grows with a little number, like 300 grows astronomically large. And the problem is that this largest, or the longest path problem is a problem for which we only have algorithms that grow like this. Every time you add a city to your question, the computation time at least doubles. And so with just 300 cities, we're already looking at fantastically large computation times. And one of the big open problems in computer science and mathematics is there a fast algorithm for this longest path problem, or does it not exist? And this is also known as the P versus NP problem, and that's one of the 7 millennium problems, and you can cash $1 million if you solve that. But I guess this 1 million now is nothing compared to the 2.4 billion that you get if you do quantum computing. But that sees how much mathematics is behind physics. That about that. And so now quantum computers are just the combination of these two fields, namely the field of quantum physics and the field of computer science. And it was Richard Feynman, famous physicist, and David Deutsch, actually, who is British and who is in Oxford. And they came up with the foundations of a quantum computer, very much like Turing did in 1936 for a computer. And just going over that quickly is like classical bits, I already said, were 0 or 1, right? It's like the detector 0 clicks or detector 1 clicks. And these quantum bits, they are right before we go into this detection mode. The qubit can be 0 and 1 at the same time. And that's sort of good enough to think about it. And if you have more qubits, you get more states at the same time. So 1 qubit we saw has 2 states at the same time. For 2 qubits we can go to 4 states, and so on. Every time we add a qubit into the mix, we see this doubling of the potential possibilities that the system can be in superposition of. Right? So when we have 300 qubits, we are in a superposition of 2 to the 300 states at the same time, which is more than the number of atoms in the universe, so astronomically large. By the way, we do have a very precise mathematical description, and I'm not going through this, but I mean, these are sort of the 0 and the 1, and they can be in a superposition, and when you measure them, you get with some outcome a 0 and with some outcome a 1, and we know exactly what it means to evolve this system to program it. This is not meant to really follow exactly, but it's just to demonstrate that we have a good mathematical description of what goes on. And one thing I do want to say is that if you have a qubit, that's somehow one of the peculiarities of quantum physics. If you have a qubit, then you cannot clone it, you cannot copy it. So that's something you can prove that is not possible. Okay, so these qubits actually, they're being built. I said, and there are several flavors that we have. There are these solid state qubits of Josephson junctions, and there's trapped ions, there's quantum dots, and there are photons, and there are even more flavors being developed. And what is problematic is that the stability of these qubits is essential for computation, and at the moment they're not stable enough, and I'm pretty sure that Barbara will say quite a bit about this in her lecture later today. And we need techniques like error correction and fault tolerance to have stable qubits built out of these noisy qubits. So several of these noisy qubits together can build a stable qubit, but this means that we have a very slow quantum computer if we have one at all, because it incurs a lot of slowdown because of this. Okay. So I already said it's very difficult and different. So imagine that you had these 300 qubits available. Now they're stable and we can do whatever we want with them for now. And imagine that you did a computation on each of these 2 to the 300 possible states at the same time. So you were doing 2 to the 300 computations for the price of one. That's fantastic. Like, you should be able to solve now all your computational problems in one go. You just let the computer do all these things. But there's a problem. How are you going to get the answer out of this machine? As I told you, if you look at it, if you measure it, then the system collapses and you basically see one random path. Right? So how do I get the answer out of this machine? I mean, if I look at it, it's gone. So it seems actually pretty useless the way it is, and it actually is. Because we need this other ingredient, we need this interference, this second ingredient of quantum mechanics that I told you, to interfere in some way the good answers interfere positively, so that when you measure you see those, whereas the paths that carry an answer that you don't care about, they have to interfere negatively and you don't see them. And then you measure. So programming is really making use of superposition and this interference. And this doesn't always work. Unfortunately, for some problems it is not at all useful, but sometimes it is, and that's what we're trying to understand. And I like this sort of parallel with making music, because sound also has superpositions, is waves, and they interfere, and a composer is trying to have these sound waves interfere in a way that it is beautiful, and some music comes out with harmonies and so on. That's what a composer does. And quantum computer composer, a quantum programmer, actually does the same thing. He lets these qubits interfere in such a way that useful information comes out of this machine. So that's sort of a parallel there with composing. So how does a program look like? Well, classically, you can have these three operations, namely NOT gates, AND gates, and OR gates. And this is exactly, by the way, how your computer works with transistors. They sort of can implement these types of gates. And when you have them available, you can do any computation that you want. Quantumly, luckily, there's also a theorem that says if you have these three gates, and this gate we have already seen, this is this beam splitter, this piece of glass that generated this superposition. But when you have another gate called a control NOT, which is actually a classical gate that, depending on whether this bit is a 0, is a 1, changes the value of this bit, it toggles it. So it's a control NOT. So these two gates you should understand by now. This is another one which is a rotation, which I haven't discussed, But you can imagine that there's another operation you can do on single qubits called the rotation over an angle pi over 4. If you have these 3 gates available for you, then just like the classical case, you can build any quantum computation by piecing them together in the right way. Okay, so that's good for experimentalists because they only have to implement these 3 operations and then we're good to go. Okay, so here's a typical quantum circuit. Like it has these 3 operations in them and they're pieced together. So here we have an input of a bunch of bits and we have some additional memory, and then these gates are operated on these qubits, and then at the end of the day you measure these qubits here at the end of the circuit, and they are zeros and ones, and if you did things correctly they will give you the answer to the problem that you were interested in. So this is how a quantum computation looks like. And for example, this Google experiment was nothing else like this. They just randomly put these gates in there, these Hadamard rotations and C-naughts in a random way, and they measured what came out. So they just ran a random circuit and looked at the distribution that came out. That's all they did. But apparently this is very difficult if that was done on more qubits in a stable way. Okay, so this is an interesting, important slide. So we do have a couple of problems for which we know that quantum computers are fast and for which we believe they are actually faster than classical computers. The first one is that of Peter Shor, his algorithm that shows that you can factor large numbers into their prime factors, which in turn breaks a lot of modern day cryptography. So modern day cryptography is broken by quantum computers. Luckily, the same quantum mechanics can save the day due to Bennett, Brassard, and also Eckert. They came up with quantum ways of using quantum mechanics to do secure communication. Then also you can efficiently communicate using quantum internet with entanglement. And another one is that simulation of nature, like quantum chemistry and quantum materials. If you try to understand what's happening there, the formalism is in the quantum mechanical formalism, and we don't know how to solve that very well on a classical computer, although the talk after me will attempt to do that using machine learning. But quantum computers, I hope, are better at doing this in the long run, because this quantum state can be stored perfectly in your quantum machine. And then last, there are also optimization problems and in machine learning where you can see some speed ups probably happening. So let me give you an example of a quantum algorithm. I can still run a little bit, I think. And this is sort of an example of how a quantum algorithm looks like. And imagine this following situation where you are doing the following thing called a random walk, which is the following. So we are here at the starting point and we flip a coin, and with probability 1/2, if it's heads we go to the right, and if it's tails we go to the left. So probability 1/2 we go left, probability 1/2 we go right. For example, you are in a city and you drank a lot and you have no idea where your hotel is anymore, and you also don't know the address, but you do know that if you're in front of it you will surely recognize it. So one way of going about is flip a coin, go to the end of the street and let the coin decide whether you go, which way you go, and you continue like that until you reach your hotel. This sounds like very stupid, and probably it's not the right thing to do if you're drunk and want to find your hotel, but a lot of algorithms though work like this and are working very well. So these random walk algorithms work very well. So here we have an example on the line where indeed with probability 1/2 you go left and right, and so let's repeat that, left and right, wherever you are with probability 1/2, and then when you look at the probability distribution after t steps where you are, the probability that you are at a certain position, it evolves like this, and you can see that still the highest probability is that you haven't moved at all, that you're back to where you began, but still there is a decent probability still of about square root away from where you started. And indeed, so with some reason, decent probability you have actually moved square root away to the right and to the left. Now let's do the same thing quantumly and not flip a coin, but do this in superposition. So with not with probability, but with amplitude, we say 1 over, well, sort of with 1/2 you go to the left, and with 1/2 you go to the right in superposition now. So we don't measure. And then let's look what this looks like in the quantum world. And the probability now, after t steps that you have where you are on this line, it evolves like this. So after 250 steps, the situation looks completely different, right? From this side and this side. You have moved quite away from the zero, actually almost 200 steps. And the probability is highest that you are here at the ends, and not at all in the middle anymore. And what you see here is exactly this phenomenon of interference, because in superposition, still a lot of paths went to the middle point here, but they cancelled destructively against each other. So you don't see them when you measure, which means that somehow the probability that you are in the ends must be higher. And that's exactly what happens. So this interference in the middle of paths that go to the zero again, they interfere negatively with each other, and the paths that don't do that sort of interfere positively. And that's what you see happening here. And well, one more time, because it took some time to program. So you see here nicely the behavior between the two walks. This one walks much faster, the quantum one. And that's actually sort of a nice ingredient for a lot of quantum algorithms. If you look sort of under the hood of them, you see some kind of initiation of this quantum walk algorithm. And for example, the famous Grover search algorithm can be cast as that, but there are many, many more algorithms that somehow use this kind of tricks. But they're not on the line, of course, but on more complicated graphs. Okay, so which problems have a quantum speed up and which don't? That's actually kind of a very complicated question, and we need a little bit of complexity theory. How much time do I have? Yeah. So we need a little bit of complexity theory of computer science for that. And that's the following situation. Actually, the story that I'm telling you now is that we don't know a lot. We don't actually know anything about computation. But bear with me. So here we have a class called P. This is the class of problems that we can solve efficiently in polynomial time, we say. So, but these are the problems that you see, like the shortest path and things that you do on your computer every day. Then there's another big blob of problems, which are called NP, which stands not for not polynomial time, but it stands for non-deterministic polynomial time. And these problems are sort of problems we would like to solve efficiently, but we don't know how to. Like, for example, this longest path, this longest route problem that we discussed earlier on. And there's a whole slew of other problems like that we would like to solve, but we don't know how to do that efficiently. And we also have this new class now of problems that we can solve efficiently on a quantum computer, right? Because these quantum computers are coming there, and we want to know how does this quantum computing class relate to the other complexity classes like efficiently computable and this NP. And I mean, it somehow probably looks like something like this. It can do a little bit more than the efficiently computable problems, but it can probably not do all this longest path problem. And it can maybe even do things that are not even in this complexity class. Now, all of this is contained in an even larger class called P-space, where we don't care about the time that your computation takes, but only the memory it uses. And this is sort of a gigantic big class that is very inefficient, but only efficient in space usage. And it could be that P is equal to P-space. We have no proof that these two classes are different. And so it could be that the whole world looks like this. So we have no proof that it doesn't look like this. And if it looks like this, you can see everything collapses to efficiently computable, and we will have no quantum supremacy and no quantum advantage at all. Quantum computers can efficiently be simulated on a classical computer. Could be like that, but we don't believe that. So we believe it looks like this. And there's sort of other problems. Maybe you've heard of the satisfiability problem. That's sort of a similar problem like the longest route problem that somehow sits in this class NP and is the most difficult one. Okay, So this is really, the set is an often used problem that I will use also now. And so it could be that P equals P space, as I showed, and then I cannot say anything about quantum advantage because there is no quantum advantage, and sort of we can all pack our bags and do something else, though we don't believe that. But if we don't believe that, we need to have a hypothesis, an assumption that this is not the case. And this is what we have done in this work with Andris and Bainis and Subhasri Patro, Koen Leijns and Florian Speelman and Bruno Loff. Sort of 3 papers, but forget about that. So what we've done is the following. We looked at problems that are efficiently solvable in polynomial time, but we wanted to know whether they were more efficiently solvable on a quantum computer. And sort of traditionally in classical computer science there are sort of 3 problems. This is the satisfiability problem that I talked about. This is a problem of given a list of n numbers, can you find 3 in there that sum up to 0, called the 3-sum. And this is a problem called the all pair shortest path problem, and that is not just asking from point A to B the shortest path, but from any A and B in your map the shortest path between them. So these are these 3 problems. And classically a lot is known if you assume that these problems are hard, so have maximal complexity. In the case of satisfiability exponential, in the case of 3-sum n squared, and in the case of all pair shortest path n cubed as well, then you can prove with quite a lot of work that all these other problems that you see here on the slide also have optimal algorithms. So just by assuming a little bit, you get a lot of explanatory power on the world of computational problems. And what we did is we tried to make this quantum, which was not easy, but we managed. And we were able to show also for a lot of problems that we got almost tight upper and lower bounds, assuming these 3 assumptions, but then in the quantum world, making them work in the quantum world. And actually it became interesting because as you see here, you see that from these 3 problems there are arrows into this triangle collection and matching triangles, whatever they are, but all 3 assumptions say something about that. And so now our quantum assumptions also say something about this, and it better be consistent with each other. And so luckily it was all consistent with each other and everything worked out fine. So I'm very happy with this. But the drawback, or sort of the message of this is that for basically all these problems that you see here, quantum computers are not going to be useful to solve them because the gaps are so small that with this overhead and error correction and fault tolerance that I discussed, you're not seeing an advantage here anytime soon. Okay, yeah, so all 3 map there. So which problems have a quantum speedup? Difficult question. There's roughly these 3 categories: exponential speedup, polynomial speedup, and no speedup. So these are sort of the ones we should focus on, quantum chemistry and so on. And these are the ones that we won't see any help or any use in the near future. Okay. I should stop, I guess. Yeah, maybe I want to end. Let me go. So quantum crypto is something that's very important, and I'm not going to discuss, so I'm going to move forward. But I do want to say something. So I can, in the break, I can tell you a little bit about this. But somehow we were working on this topic called position verification, which I won't explain what it is, but it's somehow something very interesting. Also with people here in the audience, with Adrian Kent and Sergei, we're looking at this. But then, I'm going through this, but then somehow it turned out that we hit sort of a connection with something called gravity, namely the ADS-CFT correspondence. And for some reason, this completely remote field, different field of what we were looking at, namely of quantum gravity, has implications on what we were doing. And somehow this conjecture, if that's true, then it gave very efficient attacks. It broke basically our crypto schemes, which we think shouldn't be broken, are secure. And somehow now there's sort of tension between these 2 fields. On the one hand, we believe that our schemes are secure, which means that their theory is wrong, or their theory is right. And there's efficient schemes and there's also efficient cryptographic protocols that we didn't think were efficient. So this shows somehow a side product of quantum computation, namely that it somehow has bearing to all kinds of different fields. So I won't go through this either, unfortunately. This is another result in quantum information that disproved, and I cannot show you what exactly the statement is, but this is another result that disproves a big conjecture in mathematics called the Con's embedding conjecture, by using a lot of computer science and quantum information. A very thick paper disproves that, and so now the functional analysts have a problem, because in order to understand why their conjecture is wrong, they first have to learn computer science and quantum information and all that. So they're sort of in a narrow spot there. Anyhow, won't say anything about this either, but I want to end. Oh, I do say. Let me finish this. So Europe, guys, you should come back to Europe, but I'm preaching for the choir here probably. So we do have a European quantum software initiative that just started a few months ago between these 6 partners for the moment. Amsterdam, Copenhagen, Paris, Lisbon, Munich and Latvia, and we are setting up a European sort of cooperation or institute to somehow bundle our efforts together to develop new quantum algorithms. So summary, this is, I promise, my last slide. So it really, quantum computing merges these 2 great revolutions of quantum physics and quantum and computer science. We have like endless possibilities, like we were in the 50s, 60s. Small devices are already here, and we will hear a lot about that later today. We really need software and new algorithmic thinking to employ these devices. And there are applications in computing, crypto, and internet, and we really need more work and more ideas to come up with real quantum advantage. And then this sort of the surprising side effects that maybe in the end will be even more important than all that, could very well be, namely this link with gravity, ADS-CFT correspondence, and in mathematics, this proving of a big conjecture over there. And also, I didn't really say much about it, but by thinking about your problems with the quantum glasses on, you often can just come up with classical algorithms that actually are inspired by the quantum mechanics that solve these problems on your classical machine. And perhaps this is a nice sort of bridge to the next talk. Okay.